Okay, so far until last week, we have learned all the three laws of thermodynamics, and then also we learned how to calculate enthalpy, entropy, and the Gibbs energy for the pure component. When I say pure component, it's stoichiometric phase. So we are not really considering that much of the chemical reaction or equilibrium reaction. It's just once we know what kind of phase is existing, we just simply apply the enthalpy calculation, entropy calculation to get the Gibbs energy, okay, with temperature. And also some of the actual exercise, we try how to utilize the enthalpy of reaction to increase temperature of the system. Okay, so once you have some chemical reaction in the system, and the chemical reaction is just defined in the question, and if you know what kind is really happening, you can calculate how much enthalpy is generating, or how much enthalpy is required, or how much heat is required for those kind of chemical reaction. And we assume this is adiabatic condition, or there's certain amount of heat loss or heat gain. We can use those information to calculate the final temperature of the system. Okay? As I mentioned, in the industry, one of the big concern is the energy cost. Okay? So enthalpy is one of the most important parameter to design the process. Okay? So enthalpy is very important. And entropy is basically when you have any kind of chemical reaction, you can calculate what's the change of the entropy. Entropy can change your Gibbs energy, so it's important in terms of chemical reaction. But in general, entropy is not very important when you design some industrial process. Because enthalpy is energy, but entropy is associated inside of just the chemical reaction in the Gibbs energy. So it dictates whether your chemical reaction going to the forward or backward, but it doesn't really change the energy itself. Okay, so energy is enthalpy. Okay, so we have learned basically how to calculate the Gibbs energy, enthalpy, entropy for the pure one component system, more or less. Okay, now we're going to actually switch our Gibbs energy to solution. Okay, so when you're pure stoichiometric phase, we can calculate the Gibbs energy, but now how can you calculate Gibbs energy over solution phase? So probably you already heard about activity. Have you heard about activity? Have you heard about partial pressure of the gas phase? So we are going to actually introduce this kind of concept to describe the Gibbs energy for the solution. Okay, so this is basically chapter now 3. Solution thermodynamics. Okay, so I'll just briefly explain, okay, how we distinguish the pure stoichiometric phase and the solution phase. Okay, so for example, when you have the pure iron and pure nickel, so this is Gibbs energy of iron, Gibbs energy of nickel, yeah? And when you have the FCC solution of iron and nickel, so this is solution of the iron and nickel, FCC solution, yeah? So it's different. So when you have any kind of stoichiometric phase, the Gibbs energy, we have learned already, GI equal to GI, so for example, so molar Gibbs energy of I pure, I stoichiometric phase, not solution phase, is enthalpy of I minus T entropy of I. Yeah? And enthalpy of I no, sorry, what I'm doing. I'm already starting introducing the solution phase. So this is at 298 Kelvin, standard state, plus, and entropy I, molar entropy of I equal to entropy of I naught at 298 Kelvin plus integral Cp over the T dt from 298 Kelvin to the final temperature. Okay? So we can get the Gibbs energy of I. Okay? So if you are system, so let's assume this is my system. I have NA moles of A phase. So I have A phase only, and which have NA number of moles. Then the Gibbs energy of system, the Gibbs energy of system is simply NA times GA pure, because A is pure stoichiometric phase. It's not solution phase, yeah? So when you have the 1 mole of A, 2 moles of A, 3 moles of A, the Gibbs energy of system is increasing depending on the number of moles of the A phase times Gibbs energy of A, molar Gibbs energy of A. Is it okay? Simple, yeah? Now, how about this case? Now I have A and the B is physically mixed in the system, but this is NA moles of A and MB moles of the B. So this is my system. Okay? Then, the Gibbs energy of the system equal to NA moles of A Gibbs energy, molar Gibbs energy of A, MB moles of B, molar Gibbs energy of B. Yeah? It's just, you basically assume that there's two separate phases, which is not reacting at all. So the Gibbs energy of total should be sum of A, sum of B. Yeah? So NA, GA, pure, so stoichiometric phase, which is not solution, plus NB, Gibbs energy of B phase. Is it okay? These two is simple. Now, how about when you have the solution phase? So now, if you consider that my system is AB solution phase, which have NA plus NB moles of AB solution. Then Gibbs energy of this one is not anymore same as NA GA pure, NB GB pure phase. It should not be. There's some difference here. When you have pure A and pure B separately, when you have pure AB is mixing together as one phase, there should be some difference here. When you're mixing together, so when you have separate phase, from A point of view, I don't know whether B is existing or not in the system. I don't care, because we have no interaction. So he's alone, I'm alone. Yeah. So if you want to count all the entire energy of the system, you have to count the A part and the B part. But the Gibbs energy of A is not influenced by the B. And Gibbs energy B is not influenced by A because they don't care each other. They don't even bother whether this guy is existing or not in the system. Yeah? Because there's no interaction. Okay? But now, once you have the interaction and then make one phase, so you are in the same territory now. You are in the same house. Okay? And before you are physically in the two houses separately. So they don't see each other. But now if you make a solution phase, now you are under the one roof, you are in the same house, and then now you can see the other guy. You can start to feeling some interaction, yeah? So this guy is bothering me, then I want to just go out of the system, my house. Or if this guy is very kind to me, I want to be stick with him and watch the TV together or whatever. So I'm more stable in the house, yeah? So the energy is different, okay? So that's why the energy of AB solution is different from the energy of A and the B separate phase, yeah? So we cannot say this way. So we have to derive the new Gibbs energy function to explain, okay, how can I describe this AB solution Gibbs energy? That's what we want to learn. Okay? And typically this is expressed by this way. Okay, you expressed pure A, pure B case like this. How about, can I explain this one also similarly, like NA, and then GA plus NB. So we call this one partial of A phase in solution. So in this case, this is even molar because it's 1 mole Gibbs energy. Yeah? Partial molar Gibbs energy of A in the solution, in the given solution. Okay? So we want to have the almost same expression, just summation, but this one is not anymore pure Gibbs energy. This one actually counting some sort of interaction in the solution. But we want to make the equation very simply. So I have very simplified equation. So how about Gibbs energy of the solution phase is simply mixing of the Gibbs energy of partial Gibbs energy of A and partial Gibbs energy of B in the given solution. That's the idea. Okay. Then how can I express this GA and GB? Okay. And we're going to learn this one, but in the end, the answer is like this. GA, okay. So whenever you have any kind of phase, GI, okay, any kind of phase in the solution, because we know what's the pure Gibbs energy of A, pure Gibbs energy of B, yeah, stoichiometric phase, before it becomes solution. So how about we can something without solution plus some correction, some change, because I am now interacting with my neighbor. Okay? How can I actually express that additional part, additional interaction part? That is activity. We're going to learn this one. Okay? So we want to learn how this equation came from. That's actually the basically solution Gibbs energy, solution thermodynamics. Is okay? So now, I mean, let's assume in this way. So this is okay. I mean, at the moment, we don't know exactly why we can actually, how we can derive this kind of equation. But anyway, let's take this one. At least, system Gibbs energy for solution is not anymore same as pure A, pure Gibbs, the mixing or the physical actual mixture of A and B Gibbs energy. Certainly, this is not. We can accept that. And then we want to actually express something like this. And you have now more complex system. So when you have now A phase of NA moles, and then when you have, for example, BC solution phase of the NB plus NC, then how can I actually express this one? Yeah, this is also another question. So generally, the Gibbs energy of system, you have to count all of them, all different phase, separately, phase by phase. So A is one phase, B and C is another solution phase here. So you have two different phases basically here. So Gibbs energy of system is NA moles of Gibbs energy of A, pure, plus NB, so this solution part. So solution part we can express in this way. So NB, GB, plus NC, GC as a solution phase. And when you have the more phases, depending on whether this is stoichiometric phase or solution phase, you can just add up one by one in this way. Then you can define Gibbs energy of the system. Is okay? And at least we have to understand this one, because in the end, whenever we talk about, okay, whether my system is equilibrium state or non-equilibrium state, so whether my actually reaction is going to the forward or backward, we have to compare the Gibbs energy of system before and after. Okay? If the Gibbs energy is decreasing with the change of the by the reaction or changing of the something inside of system, then that reaction, that process is going forward, yeah? Natural process. Okay? So at least we have to know in general how we describe the Gibbs energy of the system. So when you have the stoichiometric phase, which we have learned so far, it's a very simple mixture of the Gibbs energy of A, B, or C, whatever, as separately. But when you have, once you start to have actual solution phase, now we have to consider partial Gibbs energy the solution phase is separately from the stoichiometric phase. Okay? Is it okay? Clear enough? So, today and probably tomorrow, or not tomorrow, next, on Wednesday, we're going to actually learn how to derive this equation itself. Okay? Okay. So whenever we derive some new equation in thermodynamics, people always using the ideal gas, because ideal gas is very simple, very easy to understand. At least we know already one more equation for the ideal gas, PV equal to nRT here. So we always try to test our new concept by using actually the ideal gas. Okay? So now let's start first part. Okay, so first part. So gas mixture, or this is actually gas solution. Okay, so one of solution, gas solution. The very first one is, okay, Gibbs energy. One component, gas phase. So, when you have pure nitrogen gas, the Gibbs energy of pure nitrogen gas, how can you define? So, if you look at the thermodynamic table, we have H298, S298, and heat capacity over the nitrogen gas, N2. So you can find it, okay? But those value is only apply at 1 atm partial, 1 atm condition. Because it's a standard state, 1 atm. But how this Gibbs energy can be changed depending on the pressure, that's actually important. Why we're actually doing that is, once we know the Gibbs energy change with the pressure, then when you mix the two gas phases together, then we know there's the partial pressure. So we want to actually connect that pressure with the partial pressure to derive the solution Gibbs energy directly. Okay? So we know the one of the equation, dg equal to vdp minus sdt. Do you recall this one? So let's start from this one. Okay, at constant temperature, then this is equal to vdp, and then now if you are using the ideal gas law, okay, so then we can change the v to the nRT over the p. So this will be like this. N is number of moles of the gas phase. So let's assume 1 mole of gas phase. Okay? So then dg, small g, so it's molar Gibbs energy change equal to RT d, so dp of the p equal to d ln p. Is it okay? Okay, now if I know this one, so integral dg from 1 atm to certain pressure equal to RT d ln p integral to the 1 atm to the certain pressure. Is it okay? So dg from 1 atm to certain pressure. So this means, okay, Gibbs energy of the I gas phase at certain pressure, so certain pressure, minus Gibbs energy of I phase at 1 atm pressure. And this is basically pure standard state here. standard state. At 1 atm, standard state Gibbs energy. Okay? So when you have nitrogen gas, we can find this kind of information in the thermodynamic table. Okay? At 1 atm. Equal to RT ln ln P minus RT ln 1. So second part is 0. So this will be RT ln P at certain pressure, yeah? Is it okay? So in this case, PI is the pressure over I as one component system. So I have system, all of them is occupied by the nitrogen gas. So when nitrogen gas is 1 atm, Gibbs energy of nitrogen gas is same as, so this will be GI like this, and of course in this case PI, the mole fraction of I, so this is 1 times P of your system, P total of your system, yeah. So if my system containing only 1 mole of, if my system contains only nitrogen gas, N2 gas, let's assume 1 mole of nitrogen gas. If my pressure of the system equal to 1 atm, then Gibbs energy of my nitrogen gas is same as pure Gibbs energy of the nitrogen as a standard state, because this will be 1, so it's cancelled out, yeah? So it's pure nitrogen gas at 1 atm, same, yeah? Now, if I increase my pressure of the system, if I increase the pressure of the system, then PI is going up. Am I right? PI become 2, for example. Then Gibbs energy of I is Gibbs energy of I pure plus RT ln 2. So its Gibbs energy is going up. Okay? So from the Gibbs energy point of view, if my system have the 1 atm originally, and if I push it, make it small gas phase, smaller volume, then pressure is going up, and Gibbs energy is increasing during that actually the process. So it's thermodynamically less favorable process. Yeah, because Gibbs energy is increasing with the process. Okay, the other way around. If I actually decrease the system Gibbs energy, then system pressure, total pressure is decreasing, then Gibbs energy is in general decreasing from the 1 atm Gibbs energy. So Gibbs energy become more stable phase. It's become more and more stable phase. Is it okay? So gas phase become more stable. So this can be actually easily understood. I mean conceptually, it's a little bit difficult actually understand just pure nitrogen increasing pressure or decreasing pressure. But let's thinking in this way. Okay, I have water in the system, and I have a pure H2 gas in the system. Okay. If I decrease the pressure, what will happen? H2O will be evaporate further, yeah? More evaporation happen. Because your gas is more stable. Do you get it? Because by decreasing the pressure of the system, you want to have the more gas phase because gas Gibbs energy is decreasing. Yeah? So the system can reduce its Gibbs energy in this way. Is it okay? And then if you pressurize it, then the gas want to be condensing back to the solid or liquid phase, yeah? Because with the increasing of the pressure, the Gibbs energy of gas phase is increasing very quickly, so it's a less favorable process. So it want to become either solid or liquid phase again. Okay? So important thing is this one. Okay. So we have equation now. So for the Gibbs energy of the gas phase, Gibbs energy of I over the gas phase is Gibbs energy of I standard Gibbs energy plus RT ln partial pressure by, and the partial pressure, in this case actually P total, but pressure over the I phase. So Gibbs energy is Gibbs energy of gas phase is depending on its own pressure. That's important. Is it good? At least, can you accept up to this one? Okay. Now, let's actually apply this one to the solution phase. Okay, now, 2. Gibbs energy of mixing for the gas solution. Okay, so let's just make a very ideal case. So let's assume I have A gas phase here and the B gas phase. So I have one box and then I just put actually the some barrier in the middle and then I inject A gas phase in the left side, B gas phase in the right side. Okay, and then I have NA moles of A phase and B moles of B phase. Okay. But let's make one condition here. Okay, so let's assume I have same temperature, same total pressure. Same temperature, same total pressure. Total pressure is a little bit strange, so let's just say my pressure of the A side here is the P. My pressure over the B side is also P. Same temperature, same pressure. Okay? So left side, the right side is exactly the same temperature, same pressure. But number of moles of the gas phase could be different. Okay? And under this condition, the Gibbs energy of system for this condition is NA and Gibbs energy of A plus NB Gibbs energy of B, because I have NA moles of A Gibbs energy and B moles of B Gibbs energy. Yeah? And this is pure actually. Okay? But in this case, I'm not going to say it's pure because this P can be different from the 1 atm. So when you say not, I mean it's pure, but when I say not, it means this is standard state. Okay, pure standard state. Stoichiometric phase plus on top of that standard state at 1 atm. That's what I mean. And but this may be not 1 atm. So let's just put it in this way. Is it okay? So then this will be NA according to the dedication there. Gibbs energy of A now standard state plus RT Is it okay? And then we assume that PA, PB and the temperature is all same. So this will be NA GA naught plus NB GB naught plus RT NA and then P plus NB and then P, because PA and PB is same as P. Is it okay? If the P equal to 1 atm, then basically this whole term becomes 0, yeah? The P is not 1 atm, then there will be some correction term from the standard state. Okay? Good? Okay, so now, let's just remove this barrier. And there's one assumption. No chemical reaction. So it means A and B, for example, sometimes can have the chemical reaction. So for example, if A is CO, B is oxygen gas, it can make a CO2 gas, yeah, during the mixing. But if this is the nitrogen and the argon gas, for example, which doesn't have any chemical reaction because it's inert gas, so then we can simply remove this barrier and then allow them to mixing only. No chemical reaction. So when you have no chemical reaction, it means the chemical reaction make enthalpy, yeah? There's no chemical reaction, so there's no enthalpy, no temperature change. And the volume is exactly, temperature is same, pressure is same, so when you actually mix it together, the AB will, actually the A, for example, have the 1 liter of the volume per 1 mole, B have 2 moles and then become 2 liter of the the volume was 2 liter. Then when you open actually this barrier, AB, which is 3 moles of gas, will occupy 3 liter of the system. So from the ideal gas law, PV equal to nRT, we can also assume that there's no temperature change here. Pressure and volume is same, so there's no temperature change. Is it okay? So if you don't have any chemical reaction, we can just do it in this way. Okay. Now, then if I mix it together, so basically the final one, I have certain temperature and pressure, but this temperature and pressure should be same as before. And then I have now A gas phase and the B gas phase is kind of mixing without any actually interaction. And the number of moles is Na. Number of moles A is still there. Mb, moles of the B is still there. But B can be here or A can be here, anywhere. Okay, just mixing. Okay? Then let's try to write down actually Gibbs energy of the system again. So in this case, Gibbs energy of system to same as before, NaGA plus MbGb. Yeah, you have the Na moles of A phase, Mb moles of B phase. So this is NaGA plus MbGb. And I told you actually before, okay, so when you have solution phase, because before it becomes solution phase, I don't care about V phase. A phase doesn't care about V phase. Whether it's existing or not, I don't care. Okay, that was the idea. But now it becomes solution, then I have to care about B, yeah? Because I know now B is existing. But one of the actually very nice assumption about ideal gas law is, ideal gas law point of view, there's no interaction between the gas phase. Because the distance between the particle of the gas phase is so far, so they even don't know whether A phase is existing next to the A molecule existing next to the A molecule. Okay? So that's the ideal gas law. No particle interaction, no volume. Yeah? So A, even I allow them to mixing with B, A still don't know B is existing. Okay? So Gibbs energy of A and Gibbs energy of B can be exactly the same, expressed exactly the same way as before. Okay? So this is NaGA Is it okay? This is easy. So this is exactly the same actual equation we are using as one component gas phase pressure at pressure dependent Gibbs energy for the one component gas phase, and we can do that because this is ideal gas. Okay, that's the condition. And then now I just take this pure Gibbs energy, so Na GA naught plus NB GB naught. Okay, that's good. And then let's take the second term. So RT Na so how about this PA and the PB? This is now question. PA and the PB. So this is so-called partial pressure of the system. So when you have gas phase is mixing together, then pressure, partial pressure is how much pressure can be developed by each gas component in the system. So the pressure is basically the impact energy of the gas molecule, yeah? So for example, if there's the wall here, there's the wall here, and when you're actually detecting the pressure here, the way we are really detecting the pressure is, okay, this A gas is moving this way, and each impacting on this side, yeah? And then when you actually impact it, if the impact energy can be translated to the pressure, okay, because it's force, yeah? And same thing for the B. So the partial pressure of A means, okay, how much pressure among the total, how much pressure can be really contributed by the A impact, the impact by the A molecule, A gas phase. And then partial pressure of B is also same thing, how much pressure, how much impact energy contribute from the B molecule, B gas phase, okay? So pressure, partial pressure is definitely depending on the mole fraction of each gas phase in the system. Yeah? I mean, you already learned all this one in your general chemistry, but I just remind you again. So this means PA, mole fraction of A and the P total, yeah? And same thing, PB equal to mole fraction of B, P total. And P total in this case is P, just capital P, yeah? Okay? That's the total pressure of the system. So this one become NA GA naught plus NB GB naught plus RT ln. So this part here, NA XA plus NB ln XB plus NA ln P plus NB ln P. So it becomes like this. P is mole fraction and the P total. P total in this case is same as P, yeah? Okay, so if you actually separate XA and the P in the logarithm, actually the formula, so you can have logarithm of the XA times plus logarithm of the P. So you can actually dissociate this, the mole fraction part and the total pressure part. Yeah? RT, sorry, not drawn here. Yeah, sorry, is it good? Okay. So far we didn't do any magic, yeah? So we just express equation based on the equation we know, Gibbs energy of the gas phase depending on the pressure. Okay. Now if you let's look at the two sides. So left side and the right side. So we just did only one action for this process. Okay, we had a separate phase, separate gas phase in the beginning. We just remove the bar, we remove the barrier, and allow them to mixing together. Okay. So initial state, final state. Unmixed state, mixed state. And you look at actually the Gibbs energy difference. So Gibbs energy before mixing is pure Gibbs energy mixture plus ln RT, NA, ln P, ND, ln P. Okay. After mixing, you have Gibbs energy system is mixture of the pure Gibbs energy plus RT, ln NA, ln P, ND, ln P plus additional term here. Okay. I didn't do any magic, but mathematically we can see that there's difference. Okay. Now, if you compare these two Gibbs energy, before and after actually mixing, Gibbs energy mixing. So that means Gibbs energy of the system after mixing minus Gibbs energy of system before mixing is, we call it delta G of mixing, and this delta G of mixing is same as RT NA ln XA plus NB ln XB. Because all the other term is same. Is it okay? So if I express this one as molar Gibbs energy of mixing, so I divide this one by the total number of moles of the system, which is Na plus Nb. Yeah? Then delta G of mixing equal to RT XA ln XA plus XB ln XB. Okay, so this is molar Gibbs energy of mixing for ideal gas, of course, equal to this one. And now let's go back again. So Gibbs energy, okay, Gibbs energy is H minus Ts, G equal to H minus Ts. So delta G equal to delta H minus T delta S, because temperature should be same. And that's the only way we can compare the actual, at the given process, we only consider same temperature, yeah? Okay, at the same temperature, that's equilibrium state. So at the same temperature, we are considering the difference between temperature, the Gibbs energy. So delta G of mixing is basically same as delta H of mixing minus T delta S of mixing. If you look at this term, this is temperature dependence term. Okay, and also delta H of mixing is 0 because we assume that there's no chemical reaction in this process, yeah? So two inert gas, mixing together without any chemical reaction. So there's no enthalpy change because there's no chemical reaction. Okay, delta G mixing is delta H mixing minus T delta S, but this is 0, and then this term should be corresponding to this term. Okay, and now if you're actually mixing this together, you can have very famous equation, delta S of mixing equal to minus R XA ln XA plus XB ln XB. And this is ideal case, ideal gas. So we even call this one ideal. So we call this one ideal, and in this case molar entropy of mixing. So some people say that ideal molar mixing entropy or ideal molar entropy of mixing, same. Okay? So this is positive and this is negative. Can you get it? So this is negative because XA is from 0 to 1. XB is also 0 to 1. So this term is positive, this term is positive, and T should be positive. So all the positive term, but ln XA, XA is less than 1. So this is negative term. This is negative term, this is negative term. So in total, delta G of mixing should be always negative term. Okay? So delta G is negative term. That means when you have this kind of process, gas always, when you have the unmixed gas, if you just remove the barrier between unmixed gas, it always wants to mix it together because in that way it can reduce the Gibbs energy of the system. No chemical reaction involved, but just the mixing decreased Gibbs energy of the system. Is it okay? The mixing, because it's randomness. Mixing entropy is randomness, yeah? So if you have the barrier over the gas, two different gas, if you remove the barrier, it always want to mix it, yeah? Because that make randomness. I mean, we can think about, I mean, just conceptually, or even when you look at any kind of, you know, any kind of example in your real life, you can always thinking about this one, yeah? So we have barrier over the state. I removed that barrier, and it tried to be unorganized, always mixing and making random and make more noisy, whatever. So that increased entropy. That's mixing entropy. Especially like this, there's no interaction between the gas molecule. It's a very ideal case. And if just leave them, whatever you like to do, minimize energy. It's just automatically mixing. That's basically ideal mixing entropy. Okay? And this ideal mixing entropy in this case is minus R XA ln XA XB ln XB. So ln XA ln XB is of course negative term, but now with the negative and negative, so it becomes positive. So entropy of mixing is positive. So entropy mixing means now the degree of the disorderliness become increasing by the mixing. Is it okay? You good? This is very important concept. Okay? So, in reality, whatever material you have, it's impossible to get the pure material. There's always some defect or some impurity because the ideal mixing entropy term, making randomness, or making impurity, I mean, that actually decreases the energy all the time. So you cannot make a perfect, pure material, impossible, thermodynamically. It always tries to make some defect to increase the entropy, because in that way, the Gibbs energy of your system decreasing. So energy of your actual material, the energy level become decreased. It becomes slightly negative than pure. Pure 100% actually the pure material, I'm sorry, yeah. So there's always certain amount of defect. So when you actually learn all this, probably dislocation, I'm not sure whether have you learned dislocation theory? Dislocation, little bit. So whenever you have material, there's always defect, like a vacancy, you know, some kind of the array of the vacancy, and this is dislocation. And why we have dislocation? Because pure material is less stable than the material which have a little bit of dislocation. Okay? So we can even actually theoretically calculate how much dislocation should be exist in the system, in the given pure material, okay, to stabilize that material. Okay? So that's ideal entropy. I mean, that's not theoretically ideal entropy because there's certain interaction, but all this one is driven from the entropy term, entropy of mixing. You good? Okay? So in order to actually people just show up little bit of this kind of concept in the graphically actually, so we can actually draw the couple of the actual graph. Okay? So if you look at any kind of thermodynamic book, people always draw this one. So let's draw a couple of the diagram here to show the idea of this ideal entropy and ideal Gibbs energy mixing. So I actually keep actually using both terms, ideal gas mixture or gas solution, because ideal gas, the solution is actually mixture. Okay, but when we go to the solid solution or liquid solution, we never say that solid mixture or liquid mixture. It's a real solution in this case. Okay, but when you have the gas phase, the mixture is actually solution. Gas is one phase only. There's no two phase. So gas is always mixture of the gas component is always making solution. So many people say gas mixture, but it's actually gas solution. Okay, same meaning for the gas phase. But in case of solid or liquid phase, mixture is typically representing its physical mixture, physically existing separate phase. That's mixture. And then when you say solution, it's really mixing together as one phase. That's the solution, okay? So it's a little bit different terminology. Okay, for the ideal gas solution phase, ideal gas solution, we can define, okay, let's assume this is A phase and the Gibbs B phase. And most of the time, this kind of diagram, we are using in the thermodynamics, we are using mole fraction or weight percent of the x-axis here. So if I don't say any specific, anything specific, if I just say XA or XI, so it means XB is increasing this direction. So here is A is pure A in this corner, and this corner B is pure B. So basically XB is starting from 0 to 1 at 0.5 in the middle. Of course, it's increasing this direction. So with the increasing this direction, it's become XB, and with the increasing this direction, it's become XA. It's increasing, and then it becomes pure A and pure B. Is it okay? So you have to read, you have to know how to read actually this x-axis. So if I actually have around here, my mole fraction of B equal to 0.25, 0.25, and mole fraction of A equal to 1 minus 0.25, so it's 0.75. Is it okay? And the other way around. Okay? That's how we read actually x-axis here. And then let's take this one as Gibbs energy of solution. Or typically people say Gibbs energy of the gas phase. Okay? So this part here, Gibbs energy of A gas phase. I cannot say this is standard state because it may be not 1 atm. So Gibbs energy of A, and then Gibbs energy of B at the given temperature. So T equal to certain T temperature, T1, whatever. Okay? At the given temperature, I have pure Gibbs energy of A at the given pressure is defined, certain position here, and Gibbs energy of B can be defined at certain position. Yeah? Is it okay? You good? If I mix it together, okay? So this one, this straight line between GA, GB, this is unmixed state. So this is unmixed state. Okay? When you're mixing together, the Gibbs energy is decreasing from the unmixed state because of the ideal entropy term. Okay? So we can have certain change. So this is changing this way by mixing. And this one is delta G of basically mixing. This difference. At each position, the Gibbs energy of mixing can be changed depending on the composition because we have the mole fraction of XA and XB, yeah, is inside of my equation. So it can change, and the maximum is at 0.5. I'll show you a little bit later. And then at the same temperature, now people also draw in this way. Okay, A and B. So let's take this one as XB. Instead of G, how about just say, okay, Gibbs delta G of mixing. Okay, so let's just take it. Delta G of mixing directly. Then delta G of mixing at pure A equal to 0, yeah? Okay. At B also 0, yeah? So we have 0, 0. So this is 0 basically. And then when you adjust the ideal mixture, not before mixing, so it's unmixing, unmixed state. And then when you have mixing, we have negative term. We have negative. So this one is delta G of mixing, yeah? So delta G of mixing. So this is 0. So this value, whatever this value is, this is delta G of mixing, yeah? So this is exactly the same value. So when I was actually a student, I was a little bit confusing, okay? So at 0.25, this difference here, is this going to be exactly the same as 0.25? Yes, certainly, because I just tilting this one to 0, 0, and basically recalibrating to 0, 0. So I mean, this difference should be translated exactly same value, yeah? When I was a student, I tried to really mathematically prove it. Okay, this is same, but it's the same. Okay? Okay, now, okay, delta G of mixing is delta H of mixing minus T delta S of mixing. That's what we say, yeah? So, now this is delta H of mixing and A, B, XB. Delta H of mixing is same, start from 0 and 0. And this is before mixing and even after mixing is same. So after mixing, so unmixed state, mixed state, it's same, yeah? There's no difference because delta H of mixing equal to 0 during this kind of ideal mixing. Okay? This ideal gas, ideal mixing. No chemical reaction involved so far. Okay? And now delta S of mixing. So of course it starts from 0, 0. Okay? And so before mixing equal to 0 all the time. And then when you actually mix it, now from the equation, delta S of mixing okay, so when XA and XB equal to 0.5, both of them is 0.5. We can think about already. So entropy of mixing is randomness. When you have 99 ball of A and 1 ball of B, when you have 50 of A, 50 of B, which make more randomness? I mean, when you have the equal amount of A and B balls, you can make a more random distribution of the balls, yeah? So you cannot find which ball is which ball, yeah? Okay? So when you have 0.5 mole fraction, of course, it has maximum value. So minus R 0.5 ln 0.5, 0.5 ln 0.5. So it's minus R ln 0.5. Ln 0.5 is minus ln 2. So when you do that, this is maximum at 0.5. So at 0.5. And this maximum value is R ln 2. Is it okay? Make sense? Okay, let's go back again. So so delta G of mixing equals delta H of mixing minus T delta S of mixing. Okay, when temperature is going up, what will happen? In all this actual graph, when the temperature is going up, H same. So this is T1 temperature. Sorry. So T1, T1. All this one is T1. Now let's take a T2 temperature as a red line. So enthalpy of mixing 0, regardless of temperature. Enthalpy of mixing, there's no temperature dependence term. So same. Yeah? And now Gibbs energy of mixing. Gibbs energy of mixing is H minus Ts. T is multiplied on entropy of mixing. So when the temperature is going up, this is minus T, so it's become more and more negative, yeah? So delta G become more and more negative. Okay? So what this means, So when you have, the driving force for mixing two gas together become more and more strong with increasing of temperature. It makes sense here. From the kinetic point of view. So, you have gas phase, molecule is moving. When you have higher and higher temperature, it means you are giving more and more energy to the atoms or molecule to move around. So you'll have more driving force to make a more quick mixing. Yeah, more stronger actually the trend to go to the mixing. Okay, and also if you think about now entropy point of view. So at 0 degree Kelvin, you can make a perfect pure crystal, probably, yes or no. But with the increasing of temperature, you're supposed to make more and more defect because this atom is moving and moving. So you could have more and more defect can automatically generate because of the ideal entropy of mixing. But that's actually better in terms of the Gibbs energy point of view. So Gibbs energy mixing become more and more negative with the increasing of temperature. Okay, so temperature, the effect is quite reasonably understood. Is it okay? Good. Now, this was very simple, only for the mixing, ideal mixing. We don't consider any chemical reaction. Okay, but in reality, in the most of the time, when actually dealing with all this kind of gas phase, we have to consider chemical reaction. So this is 2. Is it 2? So what is 2, 3? Sorry, let's change the title. So, chemical equilibrium of the gas solution phase. So let's assume, again, we have A phase and the B phase separately, and then let's make our phase A and the B, and let's assume there's C phase is forming too. So that means, I'm just assuming that, okay, there's chemical reaction. A plus A gas phase, B gas phase, when it mixing together, instead of having the inert mixing, now we are considering some kind of chemical reaction between A, B phase. Then it becomes 2 moles of C phase, for example, C gas phase. Okay? Let's consider this way. Okay? You good? So this is initial state. This is final state. I want to know how much A gas phase, B gas phase, and C gas phase will remain in the final state. So this is initial. Final state. I want to know what's this XA, XB, and XC. I want to know this number. So I have like NA, NB in the beginning. So for example, let's assume this way. I have 1 mole of A, 1 mole of B mixing together. Okay? And then let's assume this is negative chemical reaction. This Gibbs energy is negative at certain temperature. Okay? As this AB will react all together become C or not? That's a question. What do you think? So let's assume this reaction Gibbs energy, pure A, pure B become pure C. This reaction Gibbs energy in thermodynamic table, so you can calculate your Gibbs energy of A, pure in the Gibbs in the table. B, you can get it from the thermodynamic table. C, you can get it in the thermodynamic table. At the given temperature, you did this calculation, and this is negative value. Okay? Then, if I mix 1 mole of A, 1 mole of B, how many C you'll get in the final state. Are you going to get 2 moles of C and 0 moles of A, 0 moles of B, or not? So, let me ask you one more time. Listen very carefully. I have 1 mole of A, 1 mole of B before, okay? And then I just remove this actually barrier to make them actually mixing together and then even make a reaction, chemical reaction, okay? According to the thermodynamic table, for the pure A, B, C Gibbs energy, so I can get what's A Gibbs energy, B and C Gibbs energy, I equate that together, and then I find out that this is negative reaction. So it means, yeah, negative reaction. Then this Gibbs energy is negative by forming C phase, C gas phase. So under that condition, how many moles of C I can have in the final state, and how many moles of A and B remaining in the final state. So I'll get 2 moles of C in the final state. Anyone? I'll get 2 moles of C in the final state. Nobody? Okay, the other way. I'll get less than 2 moles of C. I'll get certain amount of A and certain amount of B will remain in the system. And I don't know. Okay. So, why do you think there will be A and B remaining, for example? Because of entropy? That's very vague, actually, the answer. Anyone else?
There is a Gibbs energy of mixing.
Gibbs energy of mixing. Why? I mean, there's Gibbs energy mixing, but why that actually changing the result?
If there are more types of gases.
There's only A, B, C.
Yes, but if there is only one gas, which is C, there is no Gibbs energy of mixing. But if there are other types of gas.
Then the energy could be lower compared to the pure C? Probably. Anyone else who say, I believe there's A and B still remaining? Why? Temperature, I assume same temperature. Same temperature. Reverse reaction. But Gibbs energy is going down in this way, but reverse reaction? This is very tricky question. If you actually ask like this to any graduate student, they're not going to answer you. They know the answer, but they're not going to answer you why. I'll give you 2 examples. This is gas state. And how about I have pure solid A, pure solid B in the system, and then it can be C or A and the B and the C, solid phase, all separate phase. This is solid, 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 all separate phase. Okay, so let's do the same thing. A solid plus B solid equal to 2 moles of C solid, and this is this delta G of reaction less than 0. I'm same thing. This is delta G of reaction less than 0. So it's delta G not, it means I'm just checking the Gibbs energy of the pure C minus pure A, pure B, yeah? Standard state, pure. That's negative. When you have this condition, do you think AB will remain here or not? A and B will remain here or not? I will still have some A and some B remain. Anyone? So, I'm not going to have any AB remaining. No? I don't know. Good. I like you. You are very frank. Okay, so think about this way. So this and this one is completely different issue. Okay? So let's think about this one. Okay, I have A and B, yeah? And by mixing two, C become low energy, yeah? So think about the Gibbs energy of system, final state. Gibbs energy of system in the final state. When you have A, B, so when you have A and B is 0, then C will have, for example, this is minus 100, minus 100. This is minus 500. Okay? Then by making C, you will become minus 200, become minus 500. Certainly lower. So let's assume I'm making only half of that. Then minus 100, minus 100, and then this will be minus 50, and minus 250. Okay? So that will make minus 350 instead of minus 500. So by making all C, you can actually reduce Gibbs energy at minimum. Is it okay? So I mean, you are basically under the mass balance condition, under the same mass of A and B, okay, without generating any new mass. You just count any different condition to minimize the Gibbs energy. Okay? You just show that, okay, I have half mole of A, half mole of B remaining, and then 1 mole of C is forming, and I have 0.1 mole of A, 0.1 mole of B remaining, and 1.8 moles of C is forming, and you just count all these different scenario, and then find what is the minimum Gibbs energy condition. Okay? That's final equilibrium state. So system, try all different things and then find it out what's the, that's equilibrium state. Okay? So according to that, I mean, of course, when you're pure C, it's minimum Gibbs energy state. Okay? This is different from this one because this is pure solid. There's no solution Gibbs energy, solution Gibbs energy of mixing, entropy of mixing. That's why I said it's right, but you don't explain exactly why. Okay, but for this one, now instead of making only C, if you make only C, the Gibbs energy of gas phase is only C phase. Okay, but if you remain a little bit of A, little bit of B, and little bit C, then you have entropy is not 0. Entropy become negative term, yeah? By mixing 3 different gas phase, you can actually generate some entropy. And that entropy become positive value, and in terms of Gibbs energy, it's a negative value because H minus Ts, okay? So it become negative. And that can count it inside of solution phase, gas is solution phase. They may reduce energy even lower than pure C. Okay? That's the idea. It's a completely different issue, yeah? You see that? Okay. So then why we have lower Gibbs energy? Let's try to write down, Gibbs energy. It's very simple. So, I don't care initial state. I want to only check what's my final state, okay? So, I'll just make all different kinds of final state and find out minimum energy state. That's the idea. So, Gibbs energy of a system at the final state equal to what? You have 3 different Gibbs energy mixture, yeah? So XA, so if this is 1 mole, so small g of the final system is XA, GA plus XB, GB plus XC, GC. Is it okay? Okay, good? And Gibbs energy of A, B, C. How can you express this one? So this is XA, GA naught plus RT ln XPA. Is it okay? And XB, GB naught plus RT ln PB plus XC GB naught ln PC. Okay, so we have to find minimum Gibbs energy condition of this one by changing this mole fraction of XA, XB, and XC. Is it okay? That's actually the problem here. And if you do that, you can do all kinds of things. And now we know the pure Gibbs energy of ABC. Not this way. At least we know thermodynamically. We know each Gibbs energy of ABC, molar Gibbs energy of ABC phase. And then if you enter it, if you just do the numerically, whatever XA, XB, and XC, you'll get the final answer. Is it okay? That's how we have to solve this problem. Okay? But it looks very tedious. How we get this one? Because eventually, what I want to actually show you here is the famous equation you have run, delta G not equal to minus RT ln K, equilibrium constant. That's actually we want to derive here. Okay? I'll show you on Wednesday. Okay? Once you know this one, you are almost finishing half of your solution thermodynamics. Any question? No? You good? Okay, see you on Wednesday.